Well, thank you all for having me here today. It's really a pleasure to get to talk about integrating voluntary and policy-induced behaviors in epidemiological models. And this is something I've been actually working on since I was a master's student many years ago, starting out thinking about management of livestock and wildlife diseases, and then really moved over to thinking about this in human epidemiology during the 2009 H1N1 outbreak. Before I go much further, I want to actually make a few disclaimers about my talk. I am the Knobloch Family Professor of Natural Resource Economics at Yale, and that's how I'm speaking to you today. This is my presentation, and these views are not that of the Biden administration or the US government. I have a ton of collaborators and co-authors. I will try to mention them as I go, but if you're left out, I apologize. There's probably an exception to every characterization I will make in this talk. And as someone who's worked on this for many years, the last 2 years have kind of been insane from the standpoint of the literature. And so if I leave out recent work, again, I apologize. I find it hard to keep up. I made this little cartoon well over a year ago now, trying to explain to people that this novel coronavirus that we were facing, it wasn't just about making people sick or killing people. It was really about understanding how this is reshaping our society and how reshaping our society reshapes the way that a pathogen like this coronavirus will spread. So a lot of the work I do, whether it's in the world of epidemics and epidemiology or natural resources or other things, what I find is the core challenge is connecting our notions of how the biophysical world works, in this case, epidemiological models, with socioeconomic dynamics. What that means is when you dig into what are those challenges, it's understanding the boundaries of the system, figuring out what's in and what's out. Every modeler knows that it's impossible to have a model where everything is responding to everything. We have to make some decisions about what to hold constant and what to be endogenous. Another key problem is how do we go from individual behaviors up to sort of macro or population level trends, observations that we can see, outcomes, and then how do those sort of macro level society-wide effects feed back to shape micro or individual level behavior. And so you often see lots of models like this of human systems feeding into natural systems. Here you can think of natural systems as sort of the classical epidemiology, and then back into human systems. But I tend to not like these figures. I tend to prefer figures that look like this. I apologize for this figure being an absolute mess. And I hope this is a crowd that appreciates how many integral signs are actually here. But the point that I'm trying to make with all of this is we're doing a lot of aggregation over a lot of heterogeneity and often over a lot of uncertainty as these feedbacks. So it's not just a matter of people to natural system, but we've got people feeding into natural systems, which is affecting the incentives, the motivations of people. Somehow we're interacting that with policy, and both how the people are seeing the natural system, what they're getting out of it, and this policy push is all feeding back into the way people respond. There's two key features that drive this data generating process for people that we need to be really careful of when we have this micro, macro, and back again phenomenon. One is we can have selection on who's being affected. This could be a case where on average, it looks like everyone's changing their behavior, but maybe only the elderly are actually changing their behavior, or maybe things are passing through different subsets of the population in sequence. But on average, when we start averaging that, we see a different effect. On the other hand, we could actually have everybody making small changes that aggregate up to big changes. And that's an intensive margin problem. And which pathway is changing that data generating process really matters, not necessarily for making an immediate short-term forecast, but certainly for thinking about how a policy or how something shaped at altering people's behavior in response to an epidemic is going to work and what the outcomes will be. So I like to start off with this notion of a really simple epidemiological model built around the susceptible and infectious recovered framework that I'm assuming most people are pretty familiar with here. But I like to break it down because what I did many years ago when I started here is I said, where can behavior fit in this model? And so where most of us have focused most of our time, including me, is on this transmission function, which I've described here as simply F, which is a function of the states of this population and perhaps an aggregation of those states into a total population of N. And we commonly write that with a form I've put up here on the slide, where we might say beta times some function of N, or betas as some function of N times susceptibles times the infectious individuals, maybe normalized by the total population, gives us our new infections. Oftentimes we just cancel those N's and we get sort of a mass action model. And then often in our recovered and disease-induced mortality infections, we make this sort of linear first order approximation where we just have a single parameter that's multiplied by the infectious class. And I call this the beta GH formation today. And the challenge with this formation is there's absolutely no space for interesting behavior in this model. So those parameters, when they're beta, G, and H, they confound everything about the biology with everything about the behavior. And most of the connections that society actually has with respect to behavioral changes, they're coming through those behavioral changes through responses to risk, et cetera. And so in this calibration, we can't really evaluate behavioral-based interventions, at least in the sense where we needed a model to do it anyway, right? So early in the COVID-19 epidemic, what you saw people doing, and frankly, well before the COVID-19 epidemic, going back to many flu models, is people would say, well, we've put behavior in and we've made sort of an adjustment downwards to beta, and therefore we got fewer cases. And it's kind of like, well, I mean, I can do a model sensitivity with a change to beta, and I didn't really need a model to tell me that. I didn't need to do something very sophisticated to know that qualitatively, if there's a lower beta in that model, that we're going to get fewer cases. But there was nothing there about like how that behavior is changing, why that behavior is changing, how the policy actually connects to lowering that beta adjustment. And so oftentimes what we see when we do this is a lot of focus on heterogeneity through agent-based models, through networks, through more compartments. And oftentimes those work like selection. And then, like I said, sort of the extensive margin. And then there's been some work in the economics literature going back at least until Kramer's work in the mid-90s, where maybe it is actually adaptation. In reality, both are happening. So let me walk through kind of a way I conceptualize some of this. Let's say we only care about cases and deaths, and we're going to look at a policy like business closures. So we've got this simple model that's generating new cases, and we're going to call these cases, we're going to assume only come through a transmission pathway I'm going to call public for right now, but you can just think of this as one potential transmission pathway. So what happens? Well, cases go down, but we also have issues related to changes in consumer demand, businesses being opened, whether or not businesses are open. Maybe this influences income, maybe this influences housing, maybe this changes household sizes, right? And by changing household sizes or group living conditions, maybe this opens or alters another pathway, which I'm calling home. And we can have many pathways here. And one of the things we know is that household size influences the probability of transmission within a household. And so this is some work I did with Jude Bam a few years ago, trying to figure out, how much related to flu about in-household transmission. And so if we're shifting houses from being relatively small houses, which they are in the US, to more, say, 20-somethings moving in with their parents because they don't want to continue living in New York City because everything is shut down, we're now changing the household sizes. So are we changing transmission dynamics in suburban and rural America? And these are questions that we need to ask. And then, we have issues with moratoria on rents and, evictions and things like that all matter for shaping these pathways. And we need to think through and have models that can actually capture that with more than just a parameter shift. We need these feedbacks. The other thing to recognize is that what I've drawn out here is not a directed acyclical graph, which means that understanding the causal relationships in these processes is really, really hard. Here's something we've been working on for years, which is what about school closures, right? School closures have been what I think of as a favorite of the epidemiological modeling community for many years, particularly related to flu. They hit the literature and the policy recommendations as soon as we saw COVID-19. But what really happens in a school closure, especially when you consider that most epidemiological models I saw of school closures, at least in the early and mid 2000s through about 2015, kids just kind of vanish and adults just kind of go about their business. So we've been really interested in how do school closures actually restructure the way people interact? Where do kids go? What do adults do? Do they stay home from work? Things like that. So we're going to say, what if we close schools? Well, one of the things we realized is that if you close schools, you might get fewer cases. That's kind of the goal. But we're not just interested in cases, we're also interested in deaths. If cases are all incredibly mild, we probably don't worry about this very much, kind of like what ultimately happened with H1N1. But that what hasn't been the case with COVID-19. So you get people in hospital, but we now have also increased childcare demands. And if we don't have offsetting childcare pathways, particularly for healthcare workers, that changes the labor supply available to hospitals. In the United States, we know that our healthcare labor force actually has about 2 or 3 percentage points higher childcare demands than our average labor force for children in the age range of 5 to 12 years old. We also have people who might be making ventilators or PPE or developing vaccines might be siphoned off to deal with children. So we've seen how that the COVID-19 pandemic and the response to it has really created a childcare crisis. This could actually affect survivability in the hospital, conditional on going to the hospital with a case of COVID-19. And so we knew from a large modeling effort that will finally come out eventually, there was a footnote about this concern about healthcare labor force, and Jude Bam and I wrote a paper in early 2020 where we basically pointed out that you have this healthcare labor force that could disappear because of childcare obligations with school closures, and you have avoided cases. So if you don't avoid any cases but lose a lot of doctors and nurses, you're probably going to wind up with more death. That's the lower right-hand corner. If you avoid a lot of cases and that doesn't somehow affect your healthcare labor force, that's great, And then there's this question of how effective do doctors, nurses, healthcare workers have to be at saving lives, including like the people cleaning up after all of this. And it turns out that they don't have to be particularly effective. And so what the colors here are showing is sort of this critical effectiveness, if you will, in order for school closures to have adverse effects on mortality from the pathogen. And so this is a number we don't know. We don't actually measure healthcare productivity in terms of life saved. We measure it in terms of hospital spending. Kind of perverse. We should probably get on the stick and figure this out. Anyhow, again, we notice that there's a lot of feedbacks in this system, making it very hard to understand causal relationships. And there's a lot of other things that are actually public health concerns that can lead to death, that can be side effects from school closures. We know that school closures bring children and adults into higher contacts. This is associated with increased rates of child abuse, domestic violence, drug and alcohol abuse, rape, et cetera, all sorts of horrible things. And, I remember in the early days of all of this saying, there is this trade-off that we need to be careful about of how many cases of child abuse are worth a mortality, from COVID-19. And that's an awful decision for policymakers to have to be thinking through, but that is actually a decision that was probably worth thinking through. That doesn't mean don't close schools, but it probably means thinking way more carefully about the childcare pathways and what that means and how we deal with children. So a lot of my early work was in the theory of combining epidemiology and economics. But I pretty much strongly believe that if we just do theory and can't confront it with data, then we're not really doing our job. So we've been looking for a lot of years about how do people voluntarily respond to infectious diseases, and then COVID-19 has really created this interesting problem of what is a voluntary response, and how do you tease apart voluntary responses from policy-induced responses? So what I'm going to call policy-induced responses here are primarily stay-at-home orders or lockdowns or shelter-in-place orders, and we're going to use those three terms synonymously. We're also going to look at in the United States emergency orders and school closures. What I'm showing you here in panel A is the time spent at home using smart device location data. So this is home dwell time. The blue graph are for counties that never received a stay-at-home order. The black graph is for counties that at some point receive a stay-at-home order. The first vertical line in panel A is when they received emergency orders. The second vertical line is the median date of stay-at-home orders. So you see people are already spending a lot more time at home by the time those stay-at-home orders come in. The big gap between March 8th and March 28th, the big dip there, we can actually look at those locations. And surprise, surprise, that's people going to Costco and Walmart, and those are our big box stores here in the US. So you can think about this as people going to like Tesco or something. This was like a major shopping spree because people were already thinking they're going to be staying home whether or not there's a stay-at-home order. And you see this trend irrespective of whether counties ultimately adopt a stay-at-home order. Panel B is sort of harmonizing time at home relative to the first case in a county. Again, we see a lot of response before counties are even getting their first case. Panel C is first case in the state. There we sort of see the bottom out of time at home. Panel D is relative to harmonized on the emergency order date. We're already starting to see a response by the time that happens. Panel E is school closures. And then panel F is the harmonized on stay-at-home orders. So what we're seeing, particularly in panel F, is the stay-at-home orders, a lot of the time at home had already happened before that came into effect. And we're seeing in all these other harmonizations, not a big difference between counties that stayed home, that had stay-at-home orders, and those that didn't. So then we went on to do what economists really like to do, which is run tons and tons and tons of regressions and try and show that our models are robust to various specifications. The upper left thing called panel A, in this paper that came out in PNAS, we in the primary part of the paper, we only run 18 models, and then you can go read the supplement that has many, many, many more. But what we see is that model 1B was our preferred specification. And this is a measure of the effect size of the percent increase in time at home. The gray area sort of showing overlap, showing that the model is incredibly robust to alternative specifications. The lower figure, panel B, is the response to school closures, where I believe models 8 and 9 were using deaths, which sort of lag, and school closures came earlier, which is why we see a smaller effect size to deaths relative to various measures of cases. And then we also ran a synthetic augmented control analysis to estimate the effect size, which actually comes out much smaller, but we think there's some issues with linearity related in that model. So we do think that's a very conservative estimate of the measure of the stay-at-home order itself. But again, that points to a lot of voluntary behavior. So then what we do is we create this notion of trying to figure out how many additional cases, this notion of a compensating case measure, how many additional cases would a county have needed to have gotten the same effect of the closure. So what does this mean? The closures actually help get people to stay at home. The stay-at-home orders have people stay at home earlier, but like how much earlier? And so if you look at the dark blue curve here, this is a counterfactual for the median county in the US. That got stay-at-home orders, of what they would have done if they hadn't gotten the stay-at-home order. The red curve is, I believe, the median county in the US, that what we actually observe, and then you can read the distance following the stay-at-home order, which is basically that near vertical line, the horizontal distance between the number of cases where that occurred and the number of cases on the solid blue line. And you see this is like on the order of 20 some odd cases. The sort of light blue greenish line is using the mean county. Now we're looking at all of this in the first wave of the epidemic, and there's certainly a lot of evidence of fatigue, pandemic fatigue, which we all know and all feel. And so how strong these responses would be later in the pandemic is also is an important question. We can then look at what's going on across the country. So what I'm showing you in panel A here is this is the number of cases a county had when it put in place a stay-at-home order. White counties never had stay-at-home orders. Black counties had 0 cases when their stay-at-home orders went into effect. And you can see that many counties acted pretty early, a few not so early. Panel B and panel C are measures of that equivalent case measure for the county. B is an absolute number, C is relative to population. And what you see is that where this is purple, these are places where the equivalent cases is very low. So the stay-at-home order probably had very little effect on the initial behavioral response. There are some important exceptions, South Florida being one of them, where that response is actually quite, the force of that stay-at-home order was quite important. You see some of that in places in Arizona and a few other counties here and there as well, sort of the Detroit area of Michigan. what we'd like to do then is take those, pass those responses back through an epidemiological model and produce a counterfactual. We've done that with H1N1 data, where we looked at purely voluntary responses, and what we found is that what looks like voluntary behavioral shifts to H1N1 probably reduced cases by about 13%. This was back, again, before the COVID-19 pandemic, which had given us pause, because at that time, a lot of the literature was saying social distancing policies would reduce cases by 10 to 20%, and we were finding this voluntary response. Now, again, it's what is voluntary? Is really great public health messaging, is that still voluntary or not? Maybe we had some of that for H1N1, but still, I think, sorting those out is really important, understanding these behavioral feedbacks. We've been doing this looking at, again, like I said, childcare, and I think I'm going to speed up and sort of skip all the details about our childcare model. Suffice to say, one of the things that we learned from that model is that the real reason to engage in a social distancing policy like a school closure is it creates an option value, and it becomes more optimal to close schools or take extreme social distancing measures if pharmaceuticals that actually help end the pandemic arrive quickly, and there's a reasonable expectation that they'll arrive quickly. And then that people will accept them when they arrive. If they're really high risk, then it might be it might not be as advantageous to adopt as extreme social distancing measures, because you're basically buying an option to end the pandemic in a less painful way. Of course, there's issues about the sort of non-proportional relationship between cases and deaths that I actually think is an issue that we need to spend a lot more time on, particularly deaths that are both related to the pandemic itself, as well as potential other avenues where responses create risks, public health risks. And then here's my little pun to end on, which I'm calling my epi-log, which is as someone who studied behavior and epidemics since the since like the mid 2000s, watching what's happened during this pandemic, I would have never even thought how important people's behavioral responses would ever be, and the wide range of goals and risks, real or perceived, that would wind up driving that behavior. So this is a really important area for us to get a better sense of what are the parameters governing behavioral responses to risk, and what risks are salient to people, to really understand how they'll respond to certain policies. One piece of work I didn't get a chance to talk about was some of our response to face mask mandates. And what we see is a bit of risk compensation going on with those, but that's also important to understand that what that means is it provides comfort to reopen an economy as well. So we really need to think through what are the different feedbacks that are driving behavior. And I think I'm going to stop there, so there's some time, a bit of time for questions before I've got to drop off.
Thank you, Eli. That was really great. So I'll open up for questions. So yeah, please do put them in the chat or raise your hands. Okay, Samuel, please go ahead.
Hey, thanks for the talk. That was really cool. Yeah, so one bit I didn't understand about the non-proportional feedback. I think you were talking about like the case to death ratio, but also there's a non-linearity in things like closing schools, because even if you think it's not a high impact measure on changing infections, if you're very close to R01, I remember a lot of the debate in March 2020 was like, oh, how effective would schools be closing schools? But then it's like, if you desperately need to push R0 below 1, and it's that last little bit, that's like, that's a very non-linear relationship to the benefit of like closing schools to the overall like suppression of the epidemic. So yeah, should you bundle that in your kind of like non-linearity of effect here?
Yeah, no, I mean, I think that's right, is that if you have something where you're able to go from a reproductive rate where a pathogen is expanding to a reproductive rate where a pathogen is starting to die out. That's certainly critical. Part of what we were thinking about, which I think is also really important to think about, is closing schools doesn't cause children to disappear, and children tend to be very important to their parents. And their parents tend to be who makes up the labor force of whether those are critical workers in healthcare or critical workers elsewhere. And as we really reef on people's daily routines, even those who are healthcare workers or those working on vaccine development or those delivering PPE, we really need to think about where those children are going and how that's restructuring society. And are we actually going to get to the goals that we want? I mean, if the goal of closing schools is to separate children and create more distance, but what winds up happening is, you know, all the kids are just together somewhere in a community schedule, a community center. Well, maybe we've avoided some of the adverse effects of child abuse or risk from closing schools, but we're probably not achieving like that as big of a depression in force of affection as we may have expected, and we're foregoing really valuable learning opportunities. The point here is there's just a lot of rich trade-offs in this space, and thinking of how epidemics restructure interpersonal relationships and what those mean for value today and in the future really matters.
As a parent, I 100% agree.
Thank you, Sam. Peter, do you want to please unmute and ask a question?
Yeah, that was a really nice talk. My question is, you showed some maps and you showed that taking action sort of depended on how many cases you had in the county. But does the county next door matter? Do you take action because the city down the road has got a big problem as opposed to a city across the country? Is there a spatial spreading of action?
Yeah, so I think so let me clarify what those maps were. That was not like a recommendation for when to take action.
Sure.
What we were measuring was how many cases a county would have had to have gotten,
yeah,
or had they not taken action to have had people stay at home just as much. Right. And so if that number is big, that implies that that county's action actually had a big effect. If that number is small, it means that actually that stay-at-home order, people were going to do it anyway. And so if that, you know, in the US, at least at the point of these data, March 2020, April 2020, people were staying home anyway. And then for a lot of people, telling them they had to stay home just sort of made them get upset. And so then they wanted to go out. If you hadn't told them to stay home, they would have stayed home. And so but I think you're exactly right that we want to think about whether it's the first case in the state, whether it's a case in, you know, a certain kilometer range, like what are the right triggers are really important. And here in the Northeast, we did some work, it was never published, thinking about commuting patterns between Connecticut, New Jersey, New York, and, you know, it really mattered, right? And one of my colleagues here in Connecticut said, we don't even need a model to forecast COVID-19 here for New Haven. All we need to do is look at New York City and lag it by 3 days. And so, I mean, I think that this is certainly important and this matters. And we see this again in the US in some of our more remote communities. You know, they were, if you look at the patterns of when epidemics come through, they come through in strange times because they're remote, and it just takes that seed where some of our well-connected communities, like it spread really quick. And I'm sure it's the same in the UK.
Okay, thank you very much.
So I think also like the important thing there is it's not just neighbor, right? It's like, what does neighbor mean?
Yes.
Right?
Yeah, it's not, you're quite right. I mean, it's not just geographical neighborhood. It might be commuting time or a railway line that links places. Yeah, that's really interesting. Thank you very much.
Thank you, Peter, for your question. And thank you, Eli, for the great presentation. I wanted to ask, will you be staying around for the discussion at 4?
Unfortunately, at 4 o'clock, I need to be in another meeting. And
okay.
That's like I have windows plus and minus that, but not right at 4 o'clock today.
Oh, Well, if you're able to stay around for any of the event or join at any point, please do. But a really big thank you from us for joining us and for giving your great presentation.